and today's talk is going to be a little bit different than our normal talks. It's going to be about machine learning and how it relates to some of the more network-related technologies. And I'm pleased to introduce Mariam. She's from ESnet, and she's also a researcher that we recently hired. So take it away, Mariam.
Thanks, Jason. So morning, everyone. Thank you again for making the time for this talk. As part of the early career, which was to investigate different machine learning problems and then applying them to network operations research, we've come up with a number of techniques and tools which are going to do part of the network problems. So today I'm going to be talking about Evian, which is a platform which we've been working over the summer, which combines intent with machine learning and network automation. So the particular use case which we were targeting was how can users or scientists do on-demand resource provisioning. So currently Evian works for this, but it is pretty flexible enough that it could be extended to further use cases in the networking environment. So, I'll go into the introduction. So this project was actually a collaboration between myself, a student, Hussein, and Anu, who works at HP. And I'll tell you a bit more about the different people who have been involved in this project as we go forward. So we'll start off with an introduction and motivation. This research is not new. We actually did a mini project called INDIRA about two years ago. So this project is kind of grown out of the lessons we've learned from the deployment of INDIRA and try to hash out the problems we faced at that time. There are a few intent-based networking projects currently being done in industry, so we've been comparing ourselves to them so that we can do better. Go into the Evian architecture and particularly the machine learning part where we talk about natural language processing and the optimization it does, and then finally results and conclusions. So if we talk about what kind of a scenario we're looking at is, we're much more focused. So this is where we're trying to define what intent is. So we're focused on user intent rather than application intent. So for example, we can have a scientist who says, I want to transfer these images generated from my ALS detector to my database as quickly as possible. So we can have a huge pipeline which goes from the detector. It does the X-ray images, and they go over a network, which is this green pipe, as quickly as possible to this image data being hosted somewhere at NERSC. Now, this pipeline changes depending on different scientists. It's a complex infrastructure. Usually what happens is that the scientists would call engineers up and set these links up in advance so that they can be ensured that whenever their detector runs, the network is always there. What engineers would do is then they have the knowledge on how they can set this up. It's usually a complex work. There are many GUI upgrades being done. So for example, Oscars is a very good example to this, where you can set up these links using Oscars, and the GUI of Oscars is continuously being updated, and it's pretty complicated to use for a scientist. So you do need to talk to an engineer for this. And there are many, many other things which might happen in the middle as well. So this is the problem statement we started with, that let's just go back to the original intent-based networking research. And the problem which this research posed was, tell me what you want me to do rather than the how. So this is what networks are actually saying. Just tell the network what you want it to do rather than how it should be able to set up the resources for it. So this is where user intent comes in. So the user intent is very similar to gathering requirements about their transfers or their jobs in a sense. So a transfer intent, for example, could have requirements such as time, the endpoints they want to talk to, if they need any encryption of the data done, the kind of bandwidth they want to set up, or the paths they want to take for the data to move across. And you can have VLANs associated with it, etc. So these intents would be different depending on the use case or the transfer they're dealing with. So there are some intent-based networking projects already in industry. So let's talk about Open Daylight, Snake, and ONOS in particular. So these are the most two well-known projects. So they basically define your intent as a state machine, and they have priorities for intent. So different users have different priorities on the network. They don't use high-level language to input intent. So it is actually kind of like another programming code you have to learn if you want to put in an intent into the network. They do conflict resolution. So when you submit an intent, the network will check whether what you're asking for is available, or is it going to be in conflict with something else, either a policy or the resources already been provisioned before. They don't use GUI, so it's pretty much command line inputs. They can detect if there's an outage event. They do resource management, etc. So these were some elements which we were comparing them against. And we did INDIRA 2 years ago, where basically we were only able to do high-level language. So the users could talk in an English language to the intent system, which would then translate it into networking commands. It could do conflict resolution, and it was trying to do some GUI intents, but there were other issues which weren't being covered by INDIRA. So this is what an intent state machine looks like. Pretty complicated to look at, but it's basically, it starts from here, where this you need to install a requirement. And then you first, the requirement is the intent. So the application has requested an intent. You compile the intent, and then it goes on to install itself onto the network. If something goes wrong, it might go to recompile itself and try installing the intent. If not, then you can just remove the intent from the list and purge it, or just tag it as a failed intent and ask the application to request it all over again. So it's it's a bit complicated to look at, but it's a typical state machine of how an intent would work on a network, kind of. Sorry, yeah. So, so INDIRA was a project which was funded under the LDRD, where Inder Monga was the PI. So it was originally his idea. And we presented the project at SC. It was very well received by network engineers and users alike. So basically what Indira did was that it gave users a GUI where they could input their statements in English. It could have a very easy to talk manner. You don't actually need to learn any programming code for this. So you just talk in English. You tell Indira what you want the network to do. Indira would then take that and automatically create code, which is then ready to run on the networks. So it used ontologies and RDF to achieve this purpose. So this was the part which was very good, but it had a lot of natural language processing, which is not exactly something which is part of network engineering research. So for that, I needed to read up a lot on how web ontologies are created and how NLP researchers do their work. So the bad part about Indira was that it was very specific to certain tools, so it wasn't very extendable. It didn't have any monitoring, no machine learning in it, and it was very difficult to deploy as well. So this is where we took that and we tried to come up with a new architecture for Evian. So basically what we've done is we've introduced a server-client renderer architecture with Evian. So we stripped it down to completely new code. We added, rather than having a natural language processing based only on ontologies, we added NLP research using machine learning for speech. So for example, this is models which use LSTMs or recurrent neural networks, and this is a very well-defined problem in natural language processing research. So we basically tapped into those tools which have already been created by them to use for networks. So we create an Evian bot which can now discuss options with users and negotiate what they want. The Evian server is able to optimize the configurations they've asked for. We've added this multi-tool capability to it. So many tools can be added to it as networks advance. It's easy to deploy, and the server-client renderer architecture allows us to decouple the different parts and optimize them separately. So the bot, the best part about this is that the bot actually communicates back to engineers before automating everything. This was what INDIRA couldn't do, but here it has a step where it comes back to the engineers and says, the user is asking for this, this is what I'm going to do, are you okay for me to do this? And the engineer can say yes or no at that point. So as an overall high-level view, this is what Evian is actually doing. So this is an example of it being deployed on, for example, ESnet. So we have a Slack API where Evian is hosted as part of the clients, and that can allow you to talk to the Evian client, which is possibly hosted in a VM, which is in the edges, ESnet edge. The Evian client can do a lot of natural language processing on its own. So it can extract entities, it can understand what the users are asking for, and then ask more questions if the users have not given all the details they want. That then can communicate onto the Evian server, which does the authentication and checks that the resources the user is asking for are available or not. If not, the Evian server can negotiate with the client of like some reduced services, just so that more intents are satisfied with a reduced QoS. The Evian server can then, if everything is good, the Evian server can then talk to orchestrators. So in this particular example, we're talking to the Sense orchestrator. So the orchestrator can then go ahead and configure the network or the resources by talking to all the controllers and the switches in the core. So to enable for us to understand this better, this is a very complicated diagram, but it basically shows us the whole thing of how Evian works. So we start off with the Slack API, which is which the users can access, and it gives them the Evian bot, which they can discuss what they want for the network to do or their intent. This is received by the Evian client. So Rasa NLU and Rasa Core is the open source natural language processing library which we use. So we didn't actually have to write any NLP code ourselves. We did actually write some of the training algorithms here, which I'll talk about. But we were able to tap into this open source code which Facebook has developed, which allows you to build natural language processing bots. So we use that, which gets the intent. Once the intent is received, the Evian client will extract the entities and find the actions what the user is asking for. So for example, if the user says, I want to move a file from here to here, the Rasa NLU will understand that moving is actually transferring. So that would be an entity, and it will understand that these are the actions I need to do. Then the Evian client would generate an RDF graph. So the RDF graph helps Evian to communicate information between the client, the server, and the renderer. So it's basically a graph which summarizes all the information the user is asking for. This RDF graph is sent over to Evian server, which will now have all the information the user is asking for. The server will use this to do policy checking and conflict checking. So if the resource they're asking for is available or not, and what the current policies are, if they are being conflicted or not. If any of this situation happens, the server can then send a negotiation back to the client. So this negotiation would go in the sense of, these are the other options available, choose 1, 2, or 3. So the user can then choose a limited QoS, for example, or a different time at which they want to run their transfers if that particular link is busy. The user can then say yes or no, or which particular choice. That which generates another RDF, which now has the updated information. That again goes back to the server. So now the server knows that all of these informations are good to go. It will then attach any network-related components to this RDF. So for example, if the client has asked for sending data as quickly as possible, the server will actually do the calculations and attach the bandwidth and any other network-related QoS to these values. So the users don't actually have to know anything about how networks work. So the RDF2 is generated here. That is then sent off to the renderer. So now the renderer knows what kind of bandwidth is being asked for, what QoS is needed, and it is now able to see what are the current tools that I have available for me to use, and then it can map those actions to those network devices. So for example, if the intent was to do the transfer from 2 points, and the renderer now has access to the sense controller, so it can then basically just generate a new RDF or a new tool, new API, which will be able to call sense with the values which were held in the RDF2. So that allows it to generate a new RDF, which basically is just programming code of the sense API. And then at that point is when Evian can come back to the engineer and say, is it okay for me to run or automate all of this? The engineer can say yes or no, and then it can go ahead and configure the resources. So it is possible to completely bypass this so that Evian does everything from start to finish, so engineers don't need to know. But it's better, from our experience, it was better that engineers have more control of what is automated on the network or not. So what this architecture allows us to do is you can add more functionality and more algorithms at different stages of how this Evian works. So for example, at the server level, we can have more optimization algorithms plugged in, or at the client level, we can have different kinds of intelligence or checks being added, or at the renderer level, we can continuously add more tools which Evian can have access to. So for example, if you want to swap out the Sense API with another orchestrator or an Oscars orchestrator, we can do that as well. So this creates a very agile network. If anybody has any questions, feel free to stop me. So basically what Evian does is that it is a mixing of many, many techniques. So the Evian bot uses Rasa open source code. This is an open source code which was done by Facebook, and it's open for anybody to use. The Evian client is hosted in a Slack API, and the server does optimization for resource management currently. And we use RDF graphs to store data across all stages. So this is an example of how the Rasa open source NLP system works. So the human comes and says, what's the weather like tomorrow? So that would generate an intent that it is a weather query. This is the machine learning part where it tries to figure out what the intent is. So it is actually assigning a percentage of what the user is actually asking for. So the highest percentage allows it to determine what the intent is. So there might be a 15% recognized intent that the user is asking for something else. But because it recognizes 93% is weather, so that's what it's going to go for. And then it identifies what are the entities which the user has given. So it says that the date they've asked for is tomorrow. So this Rasa NLU uses a whole lot of training data at the back end to allow it to understand these intent and entities. And this training data can be built over time. So it can be continuously learning as users are using it. This intent goes on to the bot, where the bot knows that the user is asking for this intent in the entities, but it does not have the information of the location for the user. So the next action the bot realizes it needs to ask is, where is this person who's asking for this information? So based on what the location is, then it can do a weather API call to the database at the back end and then tell the user what it thinks the weather is. So for example, in our case, what we did was we constructed these training data sets. So for all text, so these are the training stories which we fed into the Rasa MLU. So I want to transfer a file from this time to this time. And these are the stories which you can train your bot in advance. So it can understand that that kind of text will always have an intent transfer. And these are the entities to look for. So either a start time and an end time, or what the entity is, or you can also do file sizes, which you're looking for somewhere here. So the entity is the file size. You can also go for the unit of the file size, which the bot might want to ask. So you can build these stories over time. In our case, we had 2 intents just to transfer, and we were doing about 10 stories, which was able to give us very good results in itself. So now based on these stories, when you train the bot, you can now have an input that I want to transfer a 13.2 terabyte file at 12:34 p.m. from ANL to LBL. That the bot will take in, and it will output this kind of a JSON extracted output. So it'll understand that the intent in this input was to transfer, and the entities the user has given is a file size of 13.2, a start time, the endpoints between which they want to do the transfers. Now, all of these JSON outputs can allow the Evian bot to map it to actions. So this is another example of the different actions which Evian bot has available to it. So for example, if the bot had understood an intent of greet, the bot knows that it can either utter greet back or utter a help. If the user has asked for an intent transfer, the bot knows that it could either check for requested slots, that whether the endpoints were given or not. If the endpoints were given, then the bot can request other information, which is missing from this. So what this allows us to do is, in case the user has missed certain information about the intent, the bot is intelligent enough to ask for the information which is missing. And this can change over time. So every time the user says something different, the bot knows what to ask for. We have an example which shows how this works later on. But just to give the different RDF levels which we have, so we're very much following the descriptive versus prescriptive layer here. So the first RDF is a descriptive layer where the first sentence with the requirements comes in from the users. This is very basic English. Users don't have to know any programming code. They can just basically talk to this bot. That is converted into a second RDF, the prescriptive layer, where the Evian server is able to attach network information to what the users are asking for. So for example, again, speed is something which, or bandwidth is something users don't actually understand, but Evian server is able to put this into numbers and attach it here. And then the third RDF at the rendering layer is where you are attaching the intent to the tools which are available for it. So any transfers, doing Sense API versus Oscars versus a simple SCP could also be rendered here. So this is an example of the bot in action. So the bot says, "Hi there, how can I help you?" The user says, I would like to do a transfer." And the bot says, so the bot takes this as an intent, recognizes that the intent is transfer, but it recognizes that the endpoints are not available. At this point, the bot is asking for, from where do you want to do the transfer? And the user says, I don't know, which options do I have? So this is another intelligence where the bot can actually go into the user profile and say, these are the available endpoints you have. and then the user can drive this information forward. The bot will ask for other issues like paths to the input and the output, and any information which is missing. So for example, the size of the file, what time do you want to do the transfer, and all of this information is then taken and the bot converts it into this piece, where the information you have provided is, these are your two endpoints, this is the paths to the output and the input directories, the size file, the units you're doing, and the exact time at which you want to transfer. The bot will then say that I will go ahead and check if I could do this transfer for you. In this particular example, the server says no. So this is the negotiation phase where the bot is saying that it is not installable, but these are the other options you have. So rather than doing it at 9 p.m., you can either do it at 10 or 11 the next day, or you can just quit. So the user can say that I'd rather do it at 10, and then the bot says, okay, I'll just go ahead and tell the server to do this for you. This is a picture of our Evian working in Slack. Pretty easy to install within Slack. So this is Evian talking to the user, and Hussein was a student who was testing this out. So he was saying that I want to do this transfer, and then it can have different questions which Evian can ask. So Evian can ask, what kind of a scientific field are you working in? Hussein says, I'm in climate. So where do you want to do the transfers from? So we added this capability because we realized that some of the scientists have different security constraints, and they don't necessarily know how to define these security constraints. So we wanted to do this so that the server could actually attach these themselves. So for example, for climate, we can attach different security policies during the transfers. So Evian is turning into a deployment tool. The hope is that it can turn into something which ESnet finds useful. So the stage 1 was INDIRA, which was 2 years ago. But in stage 2, where we're currently at, we have added new features to create this tool for scientists. So very specific, we're very focused on users here. And it adds machine learning to understand what the scientist's intent is. And then the third and final stage of Evian would be where machine learning can also do predictions and optimization at the back end, and create best policies for the network whenever they've asked for something. So some of the results which we found so far is the bot actually talks to users very much like a human. So if the human has given you less words in the first query, the bot can drive the conversation to ask for more information from the scientist. So we created a graph of the number of words been given in the queries versus the number of responses the bot does. So the more information you can give the bot in the first instance, the less time it will come back and ask you more questions. This is one of the best graphs which we have so far. So we actually worked a lot with Kate and Eli when we were coming up with the design of Evian. So without Evian, we've kind of tried to map the kind of hours it takes when a scientist would call up the engineer to configure a network, and the network is actually configured for them. So for example, they would call up one of the engineers or submit a ticket to ESnet. Usually they do it the day before. It takes a day, or within the day they try to tackle the ticket, where if they have more questions, they can go back to the scientists and ask for more information. Once everything is done, they understand what the request is, then they actually go ahead and install the intent. So they will check for all the security policies and everything, and they will try to configure the resources for them. And this is the particular problem which Evian is dealing with. So now, because the bot is asking for the scientists for all the information, we have considerably cut down the initial time where the scientists would be submitting the ticket and asking for more and submitting whatever they want. So the bot will do all of this legwork for them. The time to understand the request might be similar, so we can build in this server capability where it can understand more what the intent is. And then because we do automation through the rendering process, where all the necessary tools are attached to it, which can do all the security policy checks and everything, this also reduces that time quite a bit where the network is actually being configured. Again, we have this option of coming back to the engineer, where the engineer has the final say to go ahead with the automation or not. So that orange bar could change depending on which option you want to go with. So ways forward, we have actually submitted a paper about this to NSTI. We, as a proof of concept, we actually connected Evian to the Sense Orchestrator, which was a project which Shin and Alex Sim from SDM are leading. They have an intent API for the Sense Orchestrator, which sets up links between the Slack group and the nurse group, I think. So basically what Evian does is Evian gets the intent from the users or the scientists. So imagine that this is a physicist. The physicist talks to Evian, converts it into an intent. The server understands what it is. And finally, the renderer would basically just write out the intent API for the Sense Orchestrator to call out. We ran into a lot of security issues when we were working on this. Firstly, the Slack client is an issue because Slack has some security protocols, which ESnet was not very happy with, but we were able to work those things out with ESnet. The server has access to orchestrator, which are other orchestrators, which might be an issue because you have different security protocols over different devices, and we might not want to give so much of control to certain tools. But what we want to do is over the next year, we want to work with the security team in ironing out these details so that we can allow Evian to talk to different devices and allow users to access Evian easily as well. We're going to be adding much more complicated algorithms for conflict and policy checking. And we can add machine learning predictions to the bot responses as well. So it can now predict in real time what the best situation for the users are if they want to do any configuration of their networks. What we found was the server client rendering architecture allows allows capability to decouple it quite a bit. So it's easy to change the Slack API into a GUI on top if users are much more comfortable with that. So we can just have the GUI interacting with the client if that's what is asked for. The architecture also allows us more tools to be added as time goes on into the automation. So for example, if we have an intent, the intent could easily be translated into Ansible code into the future. And I guess, yeah, everybody knows that once we're trying that, if Ansible code is there, then you can automate everything in the back end as well. And that's basically what I wanted to talk to you about. Any questions and suggestions, please feel free to tell me.
Well, thank you, Mariam, for going through that talk. Really, really interesting stuff. So I'll give everybody a reminder that we'll use the chat for asking questions if anybody wants to add any in there. Do you have, I think you said that you were going to be doing some of this at SC18. Do you want to give people any information on the booth that you're going to be in or any of the experiments you intend to run?
So we're actually not going to do a demo at SC this year because we wanted to get everything right before we did the demo. So
okay, well, that makes sense.
Yeah, so basically, because of the security issues we ran into, we couldn't actually get some parts of it working. So we wanted to check. So the aim is to get the whole thing right and tested before we can actually do the demo so that we can immediately get more users to use it.
And at current time, do you sort of have a way that people can get in contact with you if they're interested in running any of this as a demonstration on their own networks, or if they're interested in providing any information that could be useful for the research?
Yes, I should have put it here, but I guess I can add it now. So my email address is mkiran@es.net. So feel free to reach out to us on this email. We are looking for use cases, so if you have any suggestions on how we can improve the Evian toolkit. So one of the arguments for Evian is that it should be deployable for any networks. So you can have an Evian which is configured for just Internet 2 running within Internet 2, and Evian which is configured for just ESnet running here. So yeah, the more the use cases we have, we can build and train the machine learning bot to have targeted networks which they deal with.
Okay. So I'll thank you again. If anybody does have any additional questions, just put them in the chat room. And also a reminder to you, Mariam, just send me your slides. I'll make sure that I get those posted along with the recording.
Okay, great. Thank you.
All right, it looks like we don't have any additional questions. So thank you again. Oh, I'm sorry, Joe just sent one in. Joe Breen from Utah, how are you addressing the inter-domain communication between controllers?
So the Sense orchestrator was designed as an inter-domain orchestrator. So it allows you to talk to controllers which are hosted on different sites. Yeah. So basically what we're doing is we're just talking to the Sense orchestrator. And because that orchestrator can do the inter-domain communication, we just rely on that. So basically what we're doing is we're using the networking intelligent tools which are already out there and just coupling Evian with those rather than writing our own security protocols, etc. Does that answer your question?
I'll wait until Joe responds. Follow-up question from Joe: Does the Evian have to have clients at both ends?
No. So the client only exists where the user is submitting the intent from. So in I can understand. Okay, so currently Evian is only for configuring resources. So we don't actually have an inter-domain communication like going from one node to the other. We can build that into the system. So we haven't thought about this use case yet. So it's a good suggestion where we have two clients which are trying to optimize from two different ends and the server tries to mediate between the two. So this is actually a good use case for us. Thanks.
All right. Any other questions that people have? Just type them in. That answered Joe's question. All right, I think that may be it. So thank you again, Mariam. We'll get this video posted. Just a reminder to everybody, we're not going to have a chat next week, but we will again on October 12th, which is 2 weeks from now. So thanks, everybody, and have a good weekend.
Okay. I think there's one more question.
Oh, yeah, I guess there was. I'm curious why Slack versus something like Rocket Chat.
Okay, so we can do Rocket Chat. We basically just used Slack because it was easier for us to integrate Rasa and Aliu within Slack, but we can do it within Rocket Chat as well. So So one of the reasons for using Slack was because all the scientists or ESnet uses Slack, so it was the next popular choice to do.
Okay, that answered Dave's question.
Okay, great, thanks everyone.
All right, well, thanks everybody. Have a good weekend. We'll talk to everybody soon.
Okay, bye.